Hello and welcome back. Lecture 4-2, Parseval's Theorem and Power Spectrum. The objectives of today's lecture are to derive Parseval's theorem for conservation of signal energy and to plot the one-sided and two-sided power spectrum for a periodic signal. Parseval's theorem or power energy conservation theorem states that if x of t is a periodic signal, the average power in x of t is p is equal to 1 over t naught, the integral over one period, the magnitude of x of t squared dt. Or in terms of Fourier series, 1 over t naught, the integral of t naught, the magnitude of the summation from k equals negative infinity to infinity, x of k, e to the jk omega naught t, magnitude squared dt. We can also rewrite this as 1 over t naught, the integral over one period, the summation over k, and the summation over p of x of k, x conjugate of p, because remember that's how you can find magnitude squared, e to the jk omega naught t, e to the negative jp omega naught t dt. So rearranging, we can pull out the terms that are not dependent upon t and write this as the summation over k, the summation over p, x of k, x conjugate of p, 1 over t naught, the integral over one period t naught, e to the jk omega naught t, e to the negative jp omega naught t dt. And because we know complex exponentials are orthogonal, this simplifies to the summation over k of x of the magnitude of x of k squared. So we can define the two-sided power spectrum as a plot of the magnitude of x of k squared versus omega. And the two-sided power spectrum makes sense for complex x of t as well. When x of t is real valued, we can have that the magnitude of x of negative k squared is equal to the magnitude of x of k squared due to the even symmetry of magnitude. And the power can be written as 2 times the magnitude of x of k squared, and then plot a one-sided power spectrum. Note that there is nothing lost by using the one-sided power spectrum when you have a real x of t. So the one-sided power spectrum would look like the following. Here's your vertical axis. And here's your horizontal axis, omega. And this is going to be the magnitude of x of k squared. So the center value at 0 is x of 0 squared. Then at omega naught, and negative omega naught, you're going to have the magnitude of x of 1 squared. And the magnitude of x of negative 1 squared. At 2 omega naught, you're going to have the magnitude of x of 2 squared. And at negative 2 omega naught, you're going to have the magnitude of x of negative 2 squared. And at 3 omega naught, you're going to have the magnitude of x of 3 squared. And at negative 3 omega naught, the magnitude of x of negative 3 squared. So when you have a two-sided spectrum, we only have to plot from 0 on. So here's omega, and we still call the vertical axis the magnitude of x of k squared. And first thing to note is that at 0, nothing changes. So at 0, I still have the magnitude of x of 0 squared. But now all my other values are multiplied by 2. So at omega naught, I have 2 times the magnitude of x of 1 squared. And at 2 omega naught, I have 2 times the magnitude of x of 2 squared. At 3 omega naught, I have 2 times the magnitude of x of 3 squared, and so on. So once again, if x of t is equal to x of 0 plus the summation from k equals 1 to infinity, 2 times the magnitude of x of k, cosine of k omega naught, plus the angle x of k, then I can have the one-sided spectrum p equal to the magnitude of x of 0 squared plus the summation from k equals 1, 2 times the magnitude of x of k squared. Note that the oscilloscope in B200, which you'll use for lab, displays the one-sided power spectrum. But instead of showing the value of 2 of magnitude of x of k squared, which would be the absolute value at each frequency, The scope shows average power in decibels, with respect to a reference. So that would be dBV or dBm. So in lab, what you'll see is that the power in decibels is going to be 10 log base 10 of the power at the harmonic divided by the power at the reference, or 10 log base 10, 2 times the magnitude of x of k squared over 1 volt RMS squared, or 20 log 10, the square root of 2, the magnitude of x of k over 1 volt RMS in dBV. Please note that you should get the same power back whether you sum the powers over the one-sided or the two-sided spectrum. Example 1. Find the power for the following signal. X of t is equal to 5 plus cosine 2 pi 3000 t plus 2 sine 2 pi 5000 t. So the first thing we're going to do is to find the Fourier coefficients. So what we have here is that omega naught equal to 2 pi 1000 radians per second. So x of 0, the DC component, is 5, and x of 3 equals x of negative 3. This is for the cosine, and it is 1/2. And x of 5 is equal to 2 over 2j, or 1 over j. And x of negative 5 is equal to negative 2 over 2j, or negative 1 over j. So the total average power in x can be found by finding the summation from k equals negative infinity to infinity of the magnitude of x of k squared. Note that all other values for k are 0, so we would put x of k is equal to 0 else, meaning for all other values of k. So this ends up being the summation of 5 squared plus 1/2 squared plus 1/2 squared plus 1 squared plus 1 squared. So the total average power is 27.5 volts squared. Note that you could have also used x of t to get this value using what you learned in your circuits course, because we know that power is RMS squared, and the RMS value for a sinusoid is VRMS is equal to the magnitude over the square root of 2. For the DC value 5, the RMS value is just 5. So using RMS values, we would have 5 squared plus the RMS value for the cosine is 1 over the square root of 2 squared, plus the RMS value for 2 sine 2 pi 5000 t is 2 over the square root of 2 quantity squared, which will also give you 27.5 volts squared. So the two-sided spectrum, P sub k, where P sub k is equal to the magnitude of x of k squared, would look like the following, where we have 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and 5 omega naught. So this is 3 omega naught, and this is 5 omega naught. And over here we have negative 5 omega naught, negative 4 omega naught, negative 3 omega naught, negative 2 omega naught, and negative omega naught. So at 0, we're going to have 5 squared, which is 25. At 3 omega naught, we're going to have 1/2 squared. And at negative 3 omega naught, we're also going to have 1/2 squared. And at 5 omega naught, we're going to have 1 squared. And at negative 5 omega naught, we're also going to have 1 squared. So this is our two-sided power spectrum. Our one-sided power spectrum means we only have to go from 0 to 5 omega naught. So here's 3 omega naught, and here's 5 omega naught, and here is pk again, and this is our one-sided power spectrum. So nothing changes about the 0 term, so it's still 25. But now at 3 omega naught, I'm going to have 2 times 1/2 squared. And at 5 omega naught, I'm going to have 2 times 1 squared. Example 2. Find the power for the following sawtooth example. So from a prior lecture, we had found the following. We found that T naught was equal to 1 second, and omega naught was equal to 2 pi radians per second. We also found that x of 0 was equal to 0, and x of k was equal to 2j over pi k. So now the power in x can be found by summing from k equals negative infinity to infinity of x of k squared, which is equal to the summation of k equals negative infinity to negative 1 of 2 over pi k squared, plus the summation from k equals 1 to infinity of 2 over pi k squared, or I can put them together as 2 times the summation from k equals 1 to infinity of 2 over pi k squared. Pulling out the terms that do not depend on k, I'd have 2 times 4 over pi squared times the summation from k equals 1 to infinity of 1 over k squared. And without knowing the answer for that summation, this is as far as I could go at this point. So rearranging this equation, I can get that the summation from k equals 1 to infinity of 1 over k squared is equal to px times pi squared over 8. Now, we are going to use another formula for power in order to solve for the summation of 1 over k squared and to get the answer for the power. So we're going to use the other average power formula in the time domain. That is 1 over t naught equals the integral over 1 period, the magnitude of x of t squared dt, which equals 1, the integral from 0 to 1, 4t minus 2, quantity squared dt, which equals the integral from 0 to 1, 16t squared minus 16t plus 4 dt. And when we solve it, we get 4/3 volts squared. So we now know that the average power in x of t is 4/3 v squared, and I can use this to solve for the summation from k equals 1 to infinity of 1 over k squared. We can also use this to find the power in dBV. So the power in decibels would be equal to 10 log base 10 of 4/3 over 1, or 1.25 dBV. And to solve for the summation of k equals 1 to infinity of 1 over k squared, this would equal 4 over 3 times pi squared over 8. So that summation is equal to pi squared over 6. And that's actually the answer to one of your homework problems. So the two-sided spectrum will look like the following, where this is omega, and we're going to mark off 0, omega naught, 2 omega naught, 3 omega naught, and so on. And over here, negative omega naught, negative 2 omega naught, and negative 3 omega naught. So at 0, we have 0 because x of 0 was 0. And at omega naught, we're going to have the magnitude of 2 over pi squared. And at negative omega naught, we're also going to have the magnitude 2 over pi squared. At 2 omega naught, we're going to have 1 over pi squared. At negative 2 omega naught, we're going to have 1 over pi squared. And at 3 omega naught, we're going to have 2 over 3 pi squared. And at negative 3 omega naught, we're going to have 2 over 3 pi squared, and so on. So our one-sided spectrum, we're going to only label from 0, omega naught, 2 omega naught, 3 omega naught, and so on. And once again, at 0, we have 0. And at omega naught, we're going to have 2 times 2 over pi squared. And at 2 omega naught, we're going to have 2 times 2 over 2 pi squared. And at 3 omega naught, we're going to have 2 times 2 over 3 pi squared. And this concludes example 2. Example 3. Find the power for the following pulse train. Once again, this is a problem we've solved before for the Fourier series coefficients. So what we have here is that T naught is equal to 8 seconds, and omega naught is equal to pi over 4 radians per second. So what we found before is that x of k is equal to 2 when k is equal to 0, and it's equal to 2 sine of pi over 2k divided by pi over 2k, or, and we had found before that this was the 2 times the sinc of k over 2, when k is not equal to 0. So what we have is that the power in x is equal to the summation from k equals negative infinity to infinity of 2 times the sinc of k over 2 quantity squared. So now let's find the power in the time domain. The power in the time domain is going to be p is equal to 1 over t naught, the integral of 1 period over 1 period, t naught, the magnitude of x of t squared dt. So this equals 1 over 8, the integral from negative 2 to 2, 16 dt, which equals 8 volts squared. So note that it is sometimes easier to use either the Fourier series or frequency domain power definition or the time domain to get the answer. In this case, the time domain was easier. So the power in decibels is going to equal 10 log base 10 of 8 volts squared with respect to 1 volt squared, which is equal to 9 dBV. And now we're going to sketch the one-sided and two-sided power spectrum again. I'll do one-sided first. So this is going to be 0, omega naught, 2 omega naught, 3 omega naught, and so on. So at 0, we have 2 squared. At omega naught, we have 2 times 4 over pi squared. At 2 omega naught, we have 0. And at 3 omega naught, we have 2 times 4 over 3 pi squared. And notice that every even multiple is going to be 0. So if I went out to 4 omega naught would also be 0. But 5 omega naught would be 2 times 4 over 5 pi squared. So what about our two-sided spectrum? So we'd have 0, 1 omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and 5 omega naught. Or over here, negative omega naught, negative 2 omega naught, negative 3 omega naught, negative 4 omega naught, and negative 5 omega naught. So once again, at 0, we have 2 squared. At every even multiple, we have a 0. So that's a 0 at 2 omega naught, 4 omega naught, negative 2 omega naught, negative 4 omega naught. At omega naught, I'm going to have 4 over pi squared. At 3 omega naught, 4 over 3 pi squared. And at 5 omega naught, 4 over 5 pi squared. It's symmetric, so on the other side, at negative omega naught, I'm also going to have 4 over pi squared. At negative 3 omega naught, 4 over 3 pi squared. And at negative 5 omega naught, 4 over 5 pi squared. So now let's do the final example for today's lecture. Find the power for the following impulse train. We've also solved for the Fourier series coefficients for this one before. So T naught is just T naught. And omega naught is 2 pi over T naught. And we found that x of k was equal to 1 over T naught. So the power in x is equal to 1 over T naught, the integral over 1 period T naught, the magnitude of x of t squared dt, which is also equal to the summation from k equals negative infinity to infinity of the magnitude of x of k squared, which is the summation from k equals negative infinity to infinity of 1 over T naught squared. And what you should see here is no matter whether we use the time domain or frequency domain definition for average power, the answer is infinity, which tells us that this is not a power signal. However, we can still plot the one-sided and two-sided power spectrum. We'll do the two-sided first. So the two-sided P sub k ends up being 1 over T naught quantity squared for all frequencies. So it is an impulse train like this that would go on forever in both directions, where this represents 0, omega naught, 2 omega naught, 3 omega naught. And over here would be negative omega naught, negative 2 omega naught, negative 3 omega naught, and so on. And the one-sided power spectrum, at 0, I will have 1 over T naught squared. However, all other values are going to be double that. So they're going to be 2 times 1 over T naught squared. And that's the same for all of them. And this would be omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. And this concludes lecture 4-2 on Parseval's theorem and power spectrum.